Imagine the universe has a throttle. For most of human history, we assumed that throttle was easing off. Galaxies were flying apart after the Big Bang, sure, but gravity should be slowing the expansion down, like a ball thrown upward losing speed. Then we discovered something that still feels wrong. The universe isn't just expanding, it's expanding faster and faster, as if space itself has an invisible engine that keeps pressing the gas. Scientists gave that engine a name: dark energy. And for the last couple decades, the safe story has been this: dark energy is a constant, a fixed background pressure built into space. It doesn't change, it doesn't evolve, it just sits there, quietly accelerating everything forever. That's why scientists could tell a clean story about the future, and that's why this new hint is making people uncomfortable. But now, after years of more precise sky surveys, more galaxies measured, more careful cross-checks, there's a whisper spreading through cosmology. What if that safe story is wrong? What if dark energy isn't constant? What if the thing pushing the universe apart is changing with time? Because if dark energy is changing, this isn't a small tweak. It would mean we've been using the wrong ruler for the universe, the wrong timeline, the wrong forecast for the fate of everything. And it would raise a question that sounds like science fiction, but isn't. Are we watching the universe shift into a new phase? In this video, we're going to walk through the evidence carefully, without hype and without drowning in equations. We'll start with the simplest picture: what dark energy is supposed to be, and why a constant dark energy became the default answer. Then we'll look at the measurements that are making scientists uneasy, what they actually found, what changing really means, and why it's so hard to trust results at this scale. Then we'll stress test the explanations. Is this just noisy data? A subtle bias in how we measure distances? A statistical mirage that disappears with more time? Or is it the first real sign that the biggest ingredient in the universe is not what we thought? By the end, you'll understand why some researchers are excited, why others are skeptical, and why, either way, this could be the beginning of the next major rewrite in cosmology. Because when the universe changes its mind, it doesn't send a warning, it just keeps expanding. To understand why this is such a big deal, you need to know what cosmology has been leaning on for decades. Because the modern story of the universe is built on a surprisingly simple idea. If you know what the universe is made of, you can predict how its expansion should behave. Right after the Big Bang, everything was hot, dense, and packed together. As it expanded, gravity got to work. Matter pulls, it clumps. And on the largest scales, gravity should act like a kind of cosmic brake, slowing the expansion over time. That's the intuitive universe. But when astronomers started measuring distant supernova explosions in the late 1990s, they found something that didn't fit that intuition. Very distant supernovae looked dimmer than expected, as if the universe had been expanding more slowly in the past and faster later. In other words, the brake wasn't winning. Something was pushing back. And that something became dark energy, a name for whatever makes the expansion speed up instead of slow down. Now here's the key part. There are many ways you can imagine dark energy behaving. It could be a field. It could be a property of space. It could be a sign that gravity works differently across enormous distances. But the simplest option, the one that made the fewest new assumptions, was this: dark energy is constant, a fixed amount everywhere at all times. In physics language, it's often treated like a cosmological constant, an energy built into empty space itself. You don't have to explain where it comes from, you don't have to give it moving parts, and you don't have to tune it to change over time. It's the cleanest patch. And the reason it became the standard is not because it feels satisfying. Most scientists don't love it. It's because it worked. When you combine a constant dark energy with ordinary matter and dark matter, you can match a shocking amount of what we observe. The overall expansion history, the large-scale distribution of galaxies, and the patterns left in the oldest light in the universe. So the standard model of cosmology became a kind of recipe, a little bit of normal matter, the stuff stars and people are made of, a larger portion of dark matter, the invisible scaffolding that holds galaxies together, and a dominant component of dark energy, making the expansion accelerate. In that standard story, the future is almost boring in its certainty. The universe keeps expanding, faster and faster. Galaxies drift farther apart. Over cosmic time, the night sky empties. The universe grows colder, darker, more isolated. That's what a constant dark energy predicts, an endless acceleration. Which is why the new whisper is so unsettling. Because if dark energy isn't constant, if it changes, then the standard story isn't a forecast anymore, it's a temporary sketch. And the next measurement could force us to redraw the entire map. We can't put dark energy in a jar. We can't aim a detector at empty space and read off a number. So how do scientists decide whether dark energy is constant or changing? They reconstruct the universe's expansion history, like rebuilding a story from a trail of clues. Here's the first clue. Looking far away is also looking back in time. Light takes time to travel. So when we observe a galaxy 1 billion light-years away, we're seeing it 1 billion years in the past. When we look 10 billion light-years away, we're peeking into a universe that was young and still assembling its first big structures. That means the sky is not one moment, it's a timeline. And if dark energy has ever changed, it has to show up somewhere on that timeline. But we still need a way to measure distance in a universe where nothing comes with a measuring tape. So cosmologists use two kinds of tools: standard candles and standard rulers. But here's the trap. If your candle flickers or your ruler bends, the universe can look like it's changing when it isn't. A standard candle is something whose true brightness we can estimate. If you know how bright it really is, then how bright it looks tells you how far away it must be. The most famous example is a particular kind of exploding star, a supernova that, when calibrated carefully, can act like a cosmic lighthouse. These explosions let us compare the universe then to the universe now, and that comparison is one of the reasons acceleration was discovered in the first place. A standard ruler is different. Instead of brightness, it's a pattern of a known size. Early in the universe, sound waves rippled through hot plasma. When the universe cooled, those ripples froze into a preferred separation scale, like a faint spacing between galaxies that's slightly more likely than any other spacing. It's not obvious in one snapshot, but across millions of galaxies, the pattern emerges. That spacing becomes a ruler. If the ruler looks smaller, the universe has stretched more. If it looks larger, it has stretched less. With rulers and candles, scientists build a distance versus time map. They measure how much the universe has stretched at different look-back times and ask a very specific question. Which expansion history fits the data best? A constant dark energy gives a very particular curve. It's smooth, predictable. It behaves the same yesterday, today, and tomorrow. A changing dark energy would bend that curve, maybe only a little, maybe only in a certain era, but it would change the shape in a way that can't be explained just by more matter or less matter. And cosmology doesn't stop with distance. There's a second line of evidence: growth. If the expansion is accelerating, it fights gravity. Structures, galaxy clusters, filaments, the cosmic web grow differently depending on how strong that push is and when it turned on. So, surveys don't just measure where galaxies are, they measure how clumpy the universe became over time. And this is where it gets serious, because if two different methods whisper the same thing, it stops being a coincidence. This is why modern sky surveys are so powerful. They don't rely on one fragile measurement. They combine distances, patterns, and growth. They cross-check one ruler with another, one candle with another, and the whole story with the oldest light we can see, the cosmic microwave background, a snapshot of the universe when it was only about 380,000 years old. If everything agrees, dark energy looks constant. If tiny disagreements line up in the same direction across multiple methods, that's when scientists start to wonder whether the universe is telling us something new. But there's a catch. At this level, the signal is subtle. The universe is huge, our instruments are imperfect, and small biases can masquerade as deep physics. So when someone says dark energy might be changing, the real question becomes, is the universe shifting? Or are we being fooled by the hardest measurements humans have ever attempted? So what is the hint everyone's whispering about? It's not one dramatic image. It's not a single galaxy doing something impossible. It's a pattern, buried in measurements of how the universe stretched over billions of years, where the clean, safe model starts to look just slightly off. Over the last few years, DESI has been building one of the most detailed 3D maps of the cosmos ever made. Millions upon millions of galaxies and quasars spread across an enormous span of time. Then, cosmologists combine that map with other time slices of the universe. Supernova distances, weak lensing, and the cosmic microwave background, our earliest snapshot. When they do that, the standard model, constant dark energy, still fits pretty well. That's important. Nobody is claiming the universe is suddenly broken. But here's the unease. Some combinations of data fit better if dark energy is allowed to evolve with time, like an engine that isn't holding a perfectly steady throttle. In some combinations, the data prefers changing just enough to raise eyebrows, not enough to declare victory, but enough that researchers can't ignore it anymore. So why isn't this an instant headline of "Dark energy changed"? Because cosmology is where tiny biases go to masquerade as deep physics. At this level, the universe is not shouting, it's whispering. And whispers can come from places you don't expect. A subtle calibration offset between surveys, selection effects in which objects make it into a catalog, the fact that different techniques measure distance in different ways, and the uncomfortable truth that when you combine many datasets, the combination itself can create tension, even if each dataset looks fine alone. That's why the responsible stance from scientists is basically, this is deeply interesting, and we need to stress test it. What would turn this from a hint into a verdict? Independent confirmations, the same shape of evolution appearing in multiple methods. Stronger data releases pushing the signal in the same direction instead of washing it out. And checks that the effect isn't coming from one sensitive piece of the pipeline. And here's the line that matters. If the effect is real, it won't vanish as the data improves. It will sharpen. Because if the hint survives that kind of pressure, then we're not just tweaking a number. We're learning that the biggest ingredient in the universe might have a history. All right, let's assume the hint survives. Not as a headline, but as a stubborn pattern that keeps showing up no matter how many times scientists try to break it. If dark energy is changing, then dark energy stops being just a label for acceleration and starts being a thing with behavior, something with a history. So what could it be? There are a few main doors cosmologists walk through, each one unsettling in a different way. Door number 1. Dark energy is a real evolving ingredient. This is the most straightforward idea. Instead of dark energy being a fixed number baked into empty space, imagine it as something more like a field, spread throughout the universe, whose strength can change over time. Think of a field like temperature in a room. The room exists either way, but the temperature can rise, fall, and drift. It can settle, it can shift, it can behave differently in different eras. The core concept is simple. The acceleration isn't powered by a constant, it's powered by something that evolves. And if that's true, then two scary things follow immediately. First, the universe is not locked into one fate, because an evolving engine can speed up, slow down, or change character. Second, the acceleration we observe could be a temporary phase. But there's also a problem. If you introduce a new evolving ingredient, you have to explain why it waited so long to matter, why it's dominating now, why it didn't ruin everything earlier. So door number 1 is plausible, but it comes with a demand. The universe must have a mechanism, and it must be subtle enough to hide until we became good at measuring it. Door number 2. Dark energy isn't changing, our gravity is. Now we move into an idea that feels almost like heresy. What if dark energy doesn't exist as a substance at all? What if acceleration is what happens when gravity behaves differently on the largest scales? Gravity is the rule book. We trust it because it works. Inside our solar system, inside galaxies, inside clusters. But the universe is the biggest physics lab there is. So the question becomes, do the same rules apply cleanly when you zoom out to billions of light years? Modified gravity ideas basically say, maybe the equations we use are a local approximation. Maybe they're missing terms that only show up when distances get enormous, or when the universe becomes dominated by emptiness rather than matter. If that's true, then the changing dark energy signal isn't a new ingredient. It's a sign that our map of gravity is incomplete. And the reason this explanation is so serious is because it's testable in a different way. A changing ingredient affects expansion. A changing gravity rule affects expansion and the growth of structure. How fast galaxies clump, how lensing bends light, how the cosmic web thickens. So door number 2 doesn't just change a number, it changes the relationship between the universe's geometry and its structure. If door number 2 is right, then the problem isn't dark energy is weird. The problem is our deepest rule for how reality holds together might need an upgrade. Door number 3. The hint is real, but it's not dark energy at all. This is the sneakiest door, because it can look like new physics while actually being a cracked assumption. Sometimes the universe doesn't change. It exposes an assumption we didn't realize we were making. There are scenarios where you can get the illusion of evolving dark energy because something else in the model is slightly off. Maybe we've mismodeled how matter clusters at late times. Maybe there are tiny cracks in how we stitch different datasets together. Maybe something in the early universe leaves a faint fingerprint that shows up later as dark energy evolution. Or maybe one of our rulers is a little bent consistently across time. This door is not as dramatic as new physics, but it's just as important. Because if the hint is coming from assumptions, then the real discovery isn't dark energy changed. The real discovery is we finally got precise enough to see the weak point in our measurement system. And this is why cosmologists treat the current situation the way they do. They're not arguing over one answer. They're trying to figure out which door the universe is pointing at. Because whichever door is real, the universe we thought we understood gets more complicated. An evolving ingredient? A shift in gravity? Or a hidden bias that only appears when you combine the biggest datasets humanity has ever built? And here's what makes this moment feel so tense. All 3 doors lead to a universe that is less predictable than we thought. Which brings us to the part that should make you pause. Because if dark energy can change, then the future of the universe is no longer a straight line.
Not one object, everything.
Here's why changing dark energy hits different than most space mysteries. Usually, when astronomy finds something strange, It's strange in one place. A weird star, a weird galaxy, a weird signal. But dark energy is not one thing out there. It's the background behavior of the entire universe. So if it changes, it's not just an object doing something unexpected. It's reality's long-term trend shifting under our feet. Because the standard story, the one built on constant dark energy, has a clean, almost depressing predictability. Acceleration continues forever. Everything drifts apart. The cosmos becomes colder, emptier, and more isolated. But if dark energy can evolve, that predictability is gone. The universe might be in a phase, and phases end. And if the throttle can move, it can move again. Here are 3 broad futures that suddenly become possible, without even invoking sci-fi. Future number 1. The push gets stronger. If dark energy grows with time, the acceleration intensifies. Galaxies race away faster, the cosmic web thins, isolation comes sooner. In extreme versions, you get a scenario where expansion doesn't just separate galaxies, it eventually overwhelms structures themselves. First clusters, then galaxies, then solar systems. Most scientists are not claiming that's happening, but the point is, when dark energy stops being constant, futures like that move from impossible to on the menu. Future number 2. The push weakens. If dark energy fades, gravity can regain influence. Acceleration slows. The expansion could settle into something gentler. That sounds comforting until you realize what it means. It would mean we are living during a special transition era, watching a cosmic behavior that isn't permanent. And in science, when you live in a special era, it usually means your assumptions are about to break. Future number 3. The push changes sign. This is the one that feels like it should be illegal to even say out loud. If the thing pushing outward could weaken enough, the universe could stop accelerating. And if it changes further, expansion could slow drastically. And in some models, it can even reverse, turning today's outward rush into a long-term collapse. Again, no one is announcing that this is what will happen. But the terrifying point isn't which future is true. The terrifying point is that the forever acceleration story is only guaranteed if dark energy is constant. If it's changing, the universe has more than one ending. And suddenly, the biggest question isn't, what is dark energy? It's, is the acceleration we see permanent? Because if it isn't, we're not living in the final chapter of the universe's story. We're living in the middle of a plot twist. So, where does that leave us right now, today? It's important to say this clearly. Dark energy changing is not a confirmed discovery. It's not a solved case. It's a signal that might still collapse into measurement quirks once the data gets sharper. But it's also not nothing, because the pattern that's bothering cosmologists isn't coming from one noisy observation. It's emerging from the biggest maps of the universe we've ever built. Maps designed specifically to measure the expansion history with brutal precision. And that's why this moment matters. Either the universe is perfectly consistent with a constant dark energy, and we're about to prove that more firmly than ever, or we're watching the first cracks appear in the simplest cosmology model humanity has used to explain everything. And here's the part I love about this story. If the hint disappears, that's still a win. It means we learned where our measurements were fragile, and we tightened them. But if the hint survives, it means the universe is not just expanding, it's evolving in a deeper way, and the engine behind the expansion has a history. So I want to ask you something. If you had to pick one door right now, do you think this is data and bias playing tricks? Or do you think dark energy is a real evolving ingredient? Or do you think gravity itself is the thing that needs rewriting? Tell me which one you believe and why. I read the comments because in moments like this, the best part of science is watching people reason it out. Because if the universe is leaving hints, it rarely leaves just one. And if the throttle can move, then the biggest question isn't what we measured, it's what happens next. See you in the next one.